grader hasn't got the quizzes back to me yet, so we'll have them Wednesday. I don't know. As soon as he's done, I'll get him back to you. Now, before I start, is there any question about anything? Anybody have any questions about stuff?
You didn't post the homework over the weekend, correct?
There was no posted homework. I'm gonna go through something. There's two things I want to go over, but today, really with Fourier transforms and Laplace transforms, they're very similar. The big difference is with Fourier, you can use duality. It's an extremely powerful property. And also Fourier does cover the range from minus infinity to plus infinity as far as the time domain. So you have something where you get transforms that do cover all time. Now there is something called a double-sided Laplace transform that does that. We don't cover it here. That's more of an advanced topic. Usually everything we do in engineering uses single-sided Laplace transforms that we've had. Because honestly in engineering you can start the clock when you want. Usually, all right, that's not a problem. Now, today, I'm going to go through a few things that are important about doing the inverse Laplace transform, and I'm going to talk about causality and why certain things are disallowed in the real, are impossible in the actual continuous time domain, where we don't have a record, a time record, but we're moving in time. And everything we do is like input now, output now or later. Follow me? That's causality. So the first thing I want to talk about is a question that you will be asked in so many words, this type of thing. I'm going to give you something that's in the frequency domain. Here, this is going to be a simple one. It'll go from, say, minus omega b to plus omega b. It's got a magnitude of 1. We can call this h of omega. Now, that obviously is a pulse function in the frequency domain. Does everybody see that? It's a simple pulse, but now it's not in time, it's in frequency. And what this really represents, if this is omega here, is a filter property. It would be what's called an ideal low-pass filter. Here, everything between minus omega b and plus omega b can pass with an amplitude of 1, if you think about that. Everything beyond that, if this is a spectral, this is in the frequency domain, h of omega. If you put a cosine of omega naught, and omega naught was somewhere between 0 and omega b, then that cosine waveform would pass through there with no distortion, with no amplitude change. Follow me, class? How many understand that right there? All right, because this represents, it just represents some x of t going in, or x of omega here. If you have a filter with some h of t here, some h of omega, then your output here is h of t convolved with x of t, or it's simply h of omega times x of omega, and that would be the y of omega here, or my y of t. You follow me on this, class? Now, if you just think about this, if you put in a cosine waveform here, well, a cosine waveform has a transform of what? Pi times delta of omega plus omega naught plus delta of omega minus omega naught. Correct, class? How many remember that? Right? It's two delta functions. It's very easy to get. If we have that, take a look at this. If the omega naught is anywhere between 0 and omega b, or 0 and minus omega b for that matter, then the cosine waveform will be multiplied by 1, and your output is your input. Follow me? However, if the cosine waveform had an omega naught out here, or really at plus omega naught, right? Then it would be multiplied by a 0. Follow me? And you would get nothing out. How many see this? This is an ideal low-pass filter. Give me a show of hands in there. All right. Now, you could have an ideal high-pass filter. An ideal high-pass filter would look like this. It would have an amplitude of 1. There's omega b, minus omega b, and 0 here. It passes only the higher frequencies. And the lower frequencies are basically stopped. How many see this? You could also have a band pass filter. And I think you know what I'm going to do. I'll take this filter and just make it have some effective, call this minus omega B2, make that omega B2, where this would be the band of frequencies that would actually be passed. Follow me? That would be a band pass. I could have a band stop, which would just be taking what? That very filter characteristic and inverting it. Wherever the 1 is, it becomes a 0. Wherever the 0 becomes 1, right? So those are the classic, absolutely perfect filter characteristics. But can you obtain them? And if not, why not? Here's where we start looking at the properties of this. And I want you to focus on this one. So if I wanted to know what the inverse transform, really what I'm after, if that is my h of omega, what I really want to know is find out my h of t. That's what I'm after. So I want my h of t. How do I get my h of t? Anyone? You know how to do it. What's the powerful theorem we use? Duality, right? Let me go ahead and make sure everybody sees this. You'll be asked this many times. Trust me on this one. You're going to see duality coming at you many, many times. So we know what duality says if you have an x of t and it goes to some capital X of omega. That's the form, the mathematical form where the argument is omega. Duality allows us to take that mathematical form and instead of omega put in t, take this function and multiply it by 2 pi, and instead of x of t, it becomes x of minus omega. All right, class? Now that's duality. I'm putting it here. You have to know how to use this and the power of it. Now when I look at this right here, this is a pulse function. And a pulse function looks like this, right? You had that on your quiz. Right, versus t. And the pulse function, or rect, you could call it, if you'd like, you could call this a rect of t over tau. Either one. It goes to tau times the sinc, right, of omega tau over 2. Tau is the spread, correct, class? Everybody with me? I've done this one time, but I'm going to do it again, and I'll make sure everybody sees this. Now, let's go through here. We have x of t being a pulse. Rect t goes to this, which is a sinc, right? So here we have the pulse waveform going to tau times the sinc of omega tau over 2. Theorem says I take the mathematical form of this x of omega and I replace omega with t. So down here, now I have tau times the sinc, right, of t times tau over 2. Are you with me, class? I'm just taking the mathematical form, replacing omega with t, correct? Can you see it in the back? Back there? All right, what do I do over here? Now I multiply by 2 pi, and I take the mathematical form here, p tau, and t is replaced by minus omega. I've done this before, but please follow me. I'm doing it for a reason. This is so important. Everybody see this? Do I need that minus in front of the omega there? Yes or no, and why? Anyone?
No, it's symmetric.
It is an even function. What he's saying is the pulse function, any value of a pulse function for a negative value of anything, negative a, is the same as the pulse function for a positive value of a. That's called an even function. Therefore, if it's even, the minus is no effect. So I can do that. One last step I'm going to do is divide both sides by pi, or 2 pi. Now, I see here that this, right, this h of omega really is defined as what? It's simply p tau of omega, right? But tau would be equal to what? 2 omega b as I've drawn it. Is that not right, class? Yes, sir.
So, where do that 2 pi and the negative come from?
This is when we took the fundamental definitions of the transforms. I'm not going to spend too much time on this, I'll just put it here. When we had capital X of omega, right, go to the integral from minus infinity to infinity of x of t times e to the minus j omega t dt, we know that's analysis. Synthesis says x of t was 1 over 2 pi. There's where the 2 pi came from. and it's the integral from minus infinity to infinity of capital X of omega e to the plus j omega t dt. And the 2 pi really comes from the fact that we're not using f. If it was f, then the 2 pi wouldn't be there.
Okay.
And that's something you'll get when you get into your communications classes. I think Dr. Tugnate he uses f, not omega. But because we're using omega, that 2 pi appears. And I can go through the formal proof with you after class if you want. All right?
No, that makes sense.
Now, anyway, this is what happens. Now look, we have this right here, don't we? Right here, class? So what is the impulse response for this going to be? My h of t? My h of t is going to be equal to, take a look, it's tau over 2 pi, correct? But tau is the width, which is 2 omega b, right? So that means it's going to be 2 omega b over pi, or really just omega b over pi. Then it's going to be the sinc of tau, which is 2 omega b divided by 2, or just omega b times t. And that's the function. I'm going to make a point here. It's an important point. I want to make sure everybody sees this. Now what I'm saying is, if I have a filter with an x of t, with an x of omega going in, and my filter property is this. This is in the h of omega domain. Minus omega b plus omega b, and this is omega here, 1 here. Then if this is a delta function, if x of t is a delta function, my output here is going to be omega b over pi times the sinc of omega bt. Correct, class? Now look, what does this delta function look like in time? If this is time, it looks like this, right? Isn't that right? Well, what does this look like in time? Well, this looks like, this is time now. Right? And the height here would be omega b over pi. Correct, class? How many see that? What troubles you? That delta function happened at what time? T equals? It happens at 0. But this thing has got values for t less than 0. It anticipated there would be something occurring at t equals 0. Do you all see that? That's called non-causal. It anticipated an input. That is an impossibility in the real world with physical time systems. All right, if you have a system moving in real time, a sensor or something like that, and you have an output, the output can't anticipate a future event. Do you follow me? Or a past, can only look at the past record. Do you follow me on this, class? This is very, very important. Now, if you have a data record, when I was at Penn State, they used to do this. They would record, at the Space Science Labs, you would record the history of, say, I don't know, electron temperature in the ionosphere for years, something like that. Now, if you want to do filtering with ideal filters, you can do it because you have a data record. Do you follow me on this? But what this really tells me is if an impulse function strikes the input and the output is occurring for times before the input occurred, that is an impossibility. That's a non-causal system. Does everybody follow me on that? That is an impossibility. The best we can do with filters, we can get close to this, but we can never get this as a filter property. What we get is something like this. We're going to get something where we get this kind of stuff. We'll get overshoots and undershoots. We'll never get a perfect filter in the continuous time domain. Does everybody understand that? Now, if we have a data record, yes, in fact, we can do something, we get an ideal filter, but you have to have recorded data to do that. I just want to make that point. Understand, class? This is very important. So that's how you would find out what the filter response would be for an impulse, and it's always important. The second thing I'm going to say, if this is my filter response here, For any input I put in, I would take the Fourier transform of that input. You follow me? X of t, no matter what it is, and I'd multiply it by this h of omega, or this pulse function. Follow me? And once I've done that, then the product of those two would be my output. And then for that, you could do the inverse. You could, a couple of ways to do it, but that would be in the frequency domain your output. And usually, we don't make this too tough. Whenever you're really doing filter work where you have a system filter response like this, and you put inputs, outputs, if you really want to get something where you're looking for given input, given output, and you've got decaying exponentials, we do it in the Laplace domain. We don't do it in the Fourier domain. Follow me, class? Laplace is a lot easier. It's simpler to do partial fraction, expansion, and things like that. This is basically something, though, that allows us to look for functional forms. Really, you're finding out what the impulse response is for filters, ideal filters. This is what we're doing. Understand? Using duality. All right, class? Duality. Now, another thing I'm going to ask, while we're on it, we've done, I feel very confident you can handle the actual Fourier transforms because they're so much like Laplace transforms. All the properties, everything's about the same with the exception of duality. And, well, there's a few odd ones, but primarily it's the same thing. I don't know how you did the quiz, but I assume people did pretty well on that. But I want to just cover a few things using properties. This is stuff that you have to be aware of. All right. One thing, I put, this was, I'm going to answer this question. Somebody, there was forms of this question. They're all essentially the same. If you had the e to the minus alpha 1 t times the sine here of omega naught t u of t, and that was one of the things I asked you, right, on the quiz? It was either that or the cosine, correct, class?
Yes.
Well, for this one, if you think about Laplace, what is it in Laplace? Isn't it s plus a, or alpha 1 over s plus alpha 1 squared plus omega naught? Oh, sorry. I'm sorry, this is omega naught. My bad. For this one, it's omega naught, right? Isn't that right, class, for the sine? Well, the only thing you had to do to get the answer for the Fourier is simply replace s here by j omega. That's it. And that's the Fourier transform of that. Understand, class? Yes. How many remember me saying that? If you take s and turn it into j omega, if the function is has non-zero values only for t greater than 0, and that u of t guarantees it, right? Then you just take s and make it j omega. Boom, we're done. Yes, sir.
What if it didn't have the U of T on it?
Well, then you would have a function that doesn't have a Fourier transform, because when this is negative time, this thing's blowing up and going to infinity, all right? And then you would have something that doesn't have the magnitude of that would not have a finite integration value. I mean, if you integrated it, it'd be infinite, all right? So you could, now you could do this one. This is one you really think about. What if I did this, right? If that's an absolute value there, then what you end up doing is this. Now you can get the Laplace transform for positive time and do it. And then for negative time, you can basically do a funny argument where you can get the same exact value for negative time. And I really don't want to play with this one right now, but let me get to that later. I know where this fits well, but not right here. All right. I want to make sure everybody understood that one. The other one I think was the same thing, e to the minus alpha 1, let's get rid of that. Alpha 1 t times cosine of omega naught t u of t. And for that one, that was s plus alpha 1 over s plus alpha 1 squared plus omega naught squared. Right, class? This is one way to do it. You didn't have to do this. Follow me on this, everyone? I mean, remember, you see this Laplace transform, you with me? You simply take the s here and make it j omega. You could do it that way. The other alternative, if you have e to the minus alpha 1 t u of t, you know the transform of that? Multiplied by a sine, you get j over 2 times that transform x of omega plus omega naught plus x of omega minus omega naught. You could do for the same for the cosine. then you could simply take the cosine, it could e to the minus alpha 1 t u of t is 1 over omega, right? Or 1 over alpha plus j omega, and then you're going to take 1/2 times that x of omega plus omega naught and x of omega minus omega naught. They're all the same, all right, as far as the answer. Are you with me, class? Either one would get you the right answer. Now, those are simply going from a mathematical form in the time domain to the frequency domain. What we need to do is explore how to get the time domain form once you're in the frequency domain, especially if you have some general form and you want to use properties to find it. In the book, he's got something where, I'll put it down as this. This is problem 552. For this one, he has f of omega equal, I believe it's a over j omega plus b. It doesn't matter what a and b are. They can be any numerical value. You take one look at that, and you know that that's really an exponential decay, isn't it? In the time domain, it would be a, right, times e to the minus bt u of t. Isn't that correct, class? So once you have that, you could just say, it can work right in the time domain, but you know that f of t is going to be a e to the minus bt u of t. You know that. But if you have the frequency domain form, and they want, what happens if I have f of, let's see, f of, suppose they have at. Well, what does that go to? I'm just going through the properties. It would be 1 over a, right? F of omega over a. Do y'all remember that? That's scaling, correct, class? Right? How many remember that? The scaling property, you have to know these classes. Same thing with Laplace. It's the same exact thing, right? You have to know these. These are going to be coming at you all the time. Next one is, what happens if I have f of, and say I have at minus b. Let's do it this way, minus b. How do I get that over here? So the only thing I'm going to do is take this function, f of omega, wherever there's an omega, I put an omega over a, and wherever, and put a 1 over a out in front as well. Understand? That's simple scaling, nothing hard about it. All right, what about this one? How do I get that property? Well, let me just ask you before I get that one, what happens to just f of t minus a? Where does that go to? Come on. You know this one. Isn't that e to the minus j omega a times f of omega, class? It's simply what? It's an it's a phase shift, isn't it, class? That e to the minus j omega a. You with me, class, on this one? So work with me here. What is this going to be? Well, I know this, right? Think of this as like an x of t, all right? A new function. Think of it that way, all right? Now, look, if I have this functional form, but how about if I make this functional form right here, f of a times quantity t minus b over a, all right? I did it for a reason, because I call this x of t, so I don't have that scale factor a in it, right? Now, when I factor out the a, right, really what that is x of what? T minus b over a. Please take a look at that. Make sure you see what I've done. You all see what I've done there? I needed to factor out that a, right? So it'd be t minus something, not at minus something. Understand that, class? I can't do it. I can't do it right here and just say, well, b is the scale factor. It isn't, right? Because it's not t minus b, it's at minus b. What I need is t minus something by itself. So I pull out the a in front, right? And now I know for this one, this is going to scale as what? Well, I know this is the transform for this one, right? Correct, class? Now, when I have, this is x of t goes to that, think of that. T minus that is just going to be e minus j omega b over a times, and then it would be 1 over a times f of omega over a. Are you with me? And you would just take this function wherever the Omega was you'd put omega over A and you'd have a 1 over A in front of it. Understand, class? Show of hands here, how many do? I know it's Monday. Did you get your test back or something? You don't look happy, I'm sorry. Wasn't my fault on that one. All right, but just work with me on this. You're gonna have to learn this, so please, snap out of the, whatever it is you got. All right, next. Suppose, yes, sir.
Speaking of tests, do you have an approximate idea of when our first test here?
If you want to vote on it now, we can. I like to do it after I do Fourier series analysis, then you vote on when you get your first test. Because here's what's on the first test. There's convolution. Oh, you don't need to write it down, guys. You're not going to forget this. Convolution, Fourier transforms, Fourier series, and Laplace transforms. Those are the 4 areas. We haven't gone through Fourier series. We're about to start it. All right? Fourier series analysis. And that's sort of it in a nutshell. Now the hard part, in my opinion, is always convolution. Just because of the nature of the problems. The flip, shift, and integrate thing drives people nuts if there's some goofy functions. It just does. You can't help it. But that's what it'll be. All right, now I'm just showing you some of the properties. Got one more for you. Work with me on this one. So, suppose I gave you this. I gave you f of t equaled e to the minus alpha 1t cosine of omega naught t u of t. All right? First is, do we know the Fourier transform of this? Yes? Well, we can get it. Do you all agree with that one, class? Yes. All right, so that's my f of t. Now I can come up with a bunch of questions. I could say, well, what is t f of t going to be? Let's just assume this goes to a well-known f of omega. Leave it as f of omega for now. We don't care about it. We know what it is. All right, what does t f of t do, class? Think about it now. If it was S domain, if it was Laplace, it would be what? Minus d ds of f of s, right? But in this case, it's going to be what? J times the derivative. It's not a minus j, it's just j times the derivative with respect to omega of f of omega. All right? Multiplication by time, times f of t, is derivative with respect to omega, and there's a j there too. We've proved that one. We can prove it again. How many remember that? At least with Laplace, you remember you bring out that minus and take the derivative with respect to s of f of s, class? With me? All right, that's one. Now what happens, just work with me on this one so we don't mess up anymore. What happens if I have this over here? Derivative in time? Come on, you know this. If it was Laplace, what happens? Derivative in time brings out a what? S. If it's in frequency domain, brings out a j omega. Thank you. I'm going through this with you. And this is a very powerful thing to remember, because oftentimes you're going to have something in the frequency domain where if you take the derivative, it looks much like a pulse or a triangle. You can go the other way, all right? But you need to take the derivative. Follow me, class? Now, once you take the derivative, you have to remember, if that thing looks like this, I mean, that's what it would be equated to, you're going to have to divide by j omega. We did, how many remember me doing that on a couple of, at least one, right? By taking the derivative for what? The triangle function to get the transform of it. You remember that, class? All right. So remember that. That's a powerful property. I'm going to give you some of these for homework to do, to work on. Most of the stuff you're going to see is fairly obvious after you think about it. You might have to look at a table or something like that, but it's not threatening. It's not, you know, way over the top crazy. But this sort of ends Fourier transforms as far as the formal application of Fourier transforms to things. Most of the time, if you're doing things where you have input-output relationships, you're looking at Laplace transforms most of the time, with the exception of things like pulse functions, and also when you really want, if you want the Fourier transform for, or the inverse Fourier transform for something, almost always use duality. That's the way to get it. Follow me? Duality is powerful. Because you'll have the time domain, when you think about, not the frequency domain form, but take that frequency domain form and think of it as a function of time, you usually have the relationship. And then you can get, through duality, what the actual inverse relationship would be. Now, we move on to the actual Fourier series analysis. Has anybody had Fourier series analysis in here? Anybody? No? This is real powerful. Now, so far, everything we've been dealing with has been dealing with waveforms that are not periodic, they're transient, like lightning, right? They're things that are transient in nature. Periodic waveforms appear everywhere, though. When you think about it, you want to actually look, when you have a periodic waveform, you know that there's some frequency it repeats itself over, correct, class? That's called the fundamental frequency. But if you had a spectral analyzer, you would see that there's a lot of energy / power, actually power at a whole bunch of other frequencies besides the fundamental. And the way we figure out what that power is, really the power spectral density, is by using Fourier series analysis. And it's very powerful. So, first of all, here's what it says. Fourier series in a nutshell says this. If you have any periodic function, doesn't matter what it is, can be like this. Any periodic function at all in the time domain. And this is some f of t. The period is listed as cap t. It's the time over which it repeats itself. That's the period. You all know what a period, how many understand what the term period is? You should from physics and your basic circuits courses, right? That's the period of a waveform, t. Well, the actual fundamental frequency, f naught, is equal to 1 over the period of the waveform. And that's an arbitrary waveform. I just threw that up there. Could be anything. Now, the next thing that happens is the fundamental frequency in the omega domain is 2 pi f naught, or it's 2 pi over t. And this is the fundamental. Now let me keep going on this one. I want you to just follow. I want to do one thing, because that's an f and this is an f. Let me put this as x of t. This is just something, a periodic function. And the real definition of a periodic function is x of t is equal to x of t plus or minus n t, where t is the period. If you add any period, number of periods, or subtract any number of periods to the argument inside that x of t, you'll get the same waveform. Understand, class? That's what it is. Now, what Fourier series analysis allows us to do, and I'm going to do the exponential form. The book has the trigonometric form. Don't worry about that. Nobody uses it. The exponential form is the thing we all use, and here's why, at least sane people use it. If I have a function x of t that's periodic, I'm going to say that can be represented as a series. Please write this down. As an exponential series from n equals minus infinity to plus infinity of some arbitrary constant c of n. Now that c of n is a complex number generally. It's not just a real number, right? It's complex. Times e to the j n omega naught t. Now n is an integer. Omega naught is the fundamental frequency of a periodic waveform you're trying to analyze. And the trick is to get c of n. That's the coefficient we're looking for. You'll notice this is a doubly infinite series from minus infinity to plus infinity. We can limit that from actually just make it a singly infinite from 0 to infinity in a bit. But for now, work with me on this. All right? So our goal is to get c of n. And mathematically, the way you're always going to go at this thing is whenever you say something is going to be, you want to make a series representation. By the way, here's something else. This is advanced, but some of you may come into it. This doesn't have to be exponentials. That's a periodic function, isn't it, class? It's something that really could be made up of sines and cosines. Couldn't you expand that with Euler's and say that's equal to what? Cosine of n omega naught, right, t, plus j sine of n omega naught, right, t, correct? Furthermore, I can say that you could break this up into any set of functions that were called orthogonal. I'm not going to get into that now. It means if you multiply any of functions by themselves and integrate it over a period, you'll get 0. If you take this function, e to the jn omega naught t, let's let n equal 1. E to the j omega naught t would be when n equals 1. If I multiply that by e to the j and then put 2 omega naught t in there, times t, multiply the two together and integrate it over a period, you get 0. They're orthogonal, and I'm not going to go down that route right now. Just understand, the trick is these things have to be orthogonal. So if I have this right here, and I multiply both sides by e to the now j m, not n, but m omega naught t. Go ahead and do it. E to the j m omega naught t here. That's the first thing I do. This is how orthogonality really works for you. Now I take this and I integrate it over a period from 0 to t. And now I come and I'm going to integrate this over a period from 0 to t dt. And here's where the magic happens. Now, if you look at this right here, I can represent this as a sum. You can forget about the sum for now. Of e to the, really, c of n times e to the j, and it would be, let me do it this way. Make this minus, I'm going to put a minus sign there. M can be anything, but I'm going to make it minus there. So it'd be j, and it would be n minus m omega naught t dt. Are you with me? Now listen carefully. When you look at this right here, e to the j n minus m omega naught t is equal to cosine of quantity n minus m omega naught t plus j sine of n minus m omega naught t. You all agree with that? Let's just use an Euler's, correct? Now I'm going to integrate this, I put it here, from 0 to t over a period. Well, what happens when you integrate from 0 to t, integrate this from 0 to t, take this times dt, integrate this from 0 to t. What happens when you integrate any cosine or any sine over a period? What do you always get? Think about it. What's the area above and below the curve?
0.
It's 0, correct, class? As a matter of fact, when you integrate the sine or cosine for any value of omega naught t, and it's periodic, where the fundamental period is really going to be t, you'll always get 0 with one exception. If n equaled n, then you would have the cosine of 0, right? Cosine of 0 is 1, isn't it? But the sine of 0 is 0, correct? So only, you'll get a non-zero value for this only when m equals n. Follow me on this? All other values, remember that sum goes from n is minus infinity to plus infinity. Only when n equals m, this is abstract, it could be any two numbers, you pick them. Only when n equals m will this integration right here have a non-zero value. Follow me? And what will the value be? It'll be 1 integrated dt from 0 to t. It will be just cap t. As a matter of fact, this is the whole essential proof right here. So that means for this entire sum, the only thing you care about is when n equals m. Follow me? The sum goes away, and the value becomes c of m times t is equal to this. The integral of x of t times e to the minus j m omega naught t dt from 0 to t. And so you can take the t over here. And that is the value of the coefficient c of m. Now, since m is a dummy variable, I can change that back to n because it's got less humps. And that's what I'm going to do. And that's what the book does. Follow me? It doesn't matter. They're dummy variables, aren't they? It doesn't matter if it's m or n. Follow me, class? And this is fairly straightforward and simple to see. But the thing about it that bothers people, let me finish my thought here and I'll get to it. that nobody spends time explaining why that integration only exists when n equals n. Do you follow me on that? The only time it exists is when really the cosine, when you expand over the cosine, you get 1. That's the only time you get a non-zero value for all the possible values of n when it equals n. Yes, sir?
All right, so I didn't really hear why you crossed out that piece over there. Is it because n equals n?
Well, the sine of 0, what's the sine of 0? 0, right? 0 integrated is still 0, so forget about sine. It's just the cosine that survives. Understand, class? And this is so important. That's C of n, and that's the thing that goes in this series right here. So you can say this entire x of t would be equal to the summation from n equals minus infinity to infinity of C of n e to the j n omega naught t, where you evaluate C of n using that. Now I'm going to show you some tricks on this. Go ahead.
So, did you use non-periodic functions if you assume an infinite period?
Well, the problem is you have to have what are called orthogonal functions. First, it's only for periodic waveforms that we're doing this. If you had something that's called a chaos waveform or something that has no correlation, something that's just random, you're going to learn about stuff like that in random signals and systems. Then that's a different story. All right? But I'm going to tell you this much right now. The amount of mathematical papers and theories about how to choose functions for expansions, that e to the j n omega naught t, that happens to be one that is the most common and easy to use, and it gives us very important information about the frequency content. At each one of these values of n right here corresponds to that value of n right there, right? Now, if you think about at omega naught, e to the j omega naught t, you could break that up into a cosine and a sine. Do you agree with me? Cosine of omega naught t plus j sine of omega naught t, those are oscillating at the fundamental frequency. And when you look at C of n, it tells you how much of that signal, if you square it as the power density, how much of that signal is at that frequency. Then when you go to n equals 2, that's the second harmonic, and you'll see how much of the signal is at the second harmonic. When you go to n equals 5, how much is the fifth harmonic, and so forth. Understand, class? So what we're doing is, these C of n's here, n is like, you might say, omega, just it's really fractions of omega. As n gets bigger, you're taking a look at the actual spectral component for higher and higher frequencies. And that's what we're up to. So now let me show you a few tricks with this. There's a lot of tricks. Next class, I'm going to show you one that's a lifesaver, and it's not in the book. Well, it's hand-waved in the book, but it's one that I think is probably the single most important trick you can use with Fourier series analysis to get information that's meaningful. I use it all the time in my radar and EMC classes, and it beats the heck out of doing that integration. We're going to do one simple integral because you have to. So we're going to do a Fourier series analysis of a simple waveform. Just work with me on this. Remember, it has to be periodic. Let's take probably the simplest one possible. Let's assume this is my waveform. Has a height a. This is my x of t. It's periodic. Period is t. But the on time is tau, right? Now there's something you're used to seeing these kind of square waves, aren't you, class? You've done JK flip-flops, things like this, haven't you? All right, you know, square waves are really what? They're oscillators. They're a clock. They're the clock in all your devices, correct? It's a digital signal. When I look at this, there's usually something called a duty cycle or duty time that's tau over t. That's a real common thing. And that tells you the amount of on time versus the total pulse width, or the total, really, period. Usually that's 0.5, isn't it, class? For almost everything we do, about 0.5. For what you're going to find out for clocking, it's 0.5, isn't it? Or am I wrong? Sure it is, right? Now you're going to find out for things like radar, this thing will go down to really 0.015, right? It will be only 15% of the entire period will be on, all right? There'll be all sorts of reasons for that, but you're going to see this is where it changes a lot. So I'm going to say this x of t here is represented by a series n equals minus infinity to infinity of C of n times e to the j n omega naught t. The first thing I have to do is get what's called C0. Now, remember, C of n is equal to 1 over the period, right? The integral from 0 to t of x of t times e to the minus j, right? And omega naught t dt. Correct, class? I'm going to make a few comments here. Write this down. From 0 to t is true, but it can be from any starting point to any finishing point with a spacing of t. So you might as well just put down epsilon here. Right? It started at epsilon, right? And it ended at t plus epsilon. Or epsilon could be minus 0.5. It could be anything. Follow me? Most of the time when I do these, I do the integration from minus t over 2 to plus t over 2. That's my usual trick I use. Now, when I'm doing this one, I'm going to go from 0 to t just because I will start it here, I can start it here, stop it here, it doesn't matter. So now I'm going to get what c of n is. But first I have to get c of 0. That's the thing I'm going to tell you about. C0 is really the DC component. It's really the amount of the signal at DC, or the DC value. The average value of the signal is C0. And it's simply equal to 1 over the period, the integral of x of t. Well, e to the j0 is 1, so it's just integrated that dt from 0 to t. What's the average value of that signal by looking? Well, what's the integral of x of t dt? Isn't it just a times tau, right? Isn't that right, class? That's the area under this curve, right? And I have to divide that by cap t. So that would be C0. Now, what is C of n in general? Well, it would be what? 1 over t, the integral from where to where? Think about the limits. When is it non-zero? From 0 to tau, right? So I integrate from 0 to tau, just a, right, times e to the minus j and omega naught t dt. And that's going to be what? A over cap t, right? Integrate e to the minus j and omega naught t dt. I get 1 over minus j and omega naught here. Then I have to evaluate e to the minus j and omega naught t from 0 to tau. Correct, class? Right? This isn't hard to do. What do I do when I see a minus sign out in front of two limits? Do you remember? Get rid of the minus sign and flip the limits. Sure. So put this as tau. Make this 0, right? And what does that give me? That gives me a over cap t times 1 over j n omega naught. And then it's going to be 1 minus e to the minus j and omega naught tau. Just hang on for 1 second. Are you with me? You'll notice there's a j here, class. Do you all see that? I have n omega naught. Now this is true for n not equal to 0. When n is 0, you have C0. That's over here. That's what you calculate as the average value. Understand? Over here, when I look at this, I'm not going to do it today, but do you all see I could factor out an e to the minus j n omega naught tau over 2. And then I would get e to the plus j n omega naught tau minus e to the minus j, e to the plus j n omega naught tau over 2 minus e to the minus j n omega naught tau over 2. How many see that? Why would I do that? Anybody? Right. I can turn this into a sine waveform. I'll do it next time. All right. If you saw that, you're doing well. All right. I'm going to give you some homework. We're coming. Now this stuff can get nuts as far as the integration, but I'm going to show you some tricks next time. You're going to thank me. I'll get letters of thanks after in your upper level courses.